I am Sergeant Monica C. Manuel, Philippine Army Reserve, from 105th Community Defense Center, 1st Regional Community Defense Group. I live in Barangay Bayawas, Urdaneta City, Pangasinan, and I am 21 years old, born August 28, 1999 at Urdaneta City, Pangasinan. I finished my advanced ROTC at Pangasinan State University, Urdaneta Campus. I finished my ROTC Summer Camp Training 31-32 and Advanced ROTC Academic Phase Training 41-42 at Manawag, Pangasinan.
Before we start our lecture, these are our classroom instructions. First, keep your phone on silent mode. Next, if you feel sleepy, do some stretching or exercises. If you need to go to the CR, just go straight to the CR. For the safety precautions, in case of fire, go out and go to your safe meeting place. If you feel sudden earthquake, do the drop, cover, and hold. Our topic for today is about the basic map reading. The scope of our topic is definition, importance, and caring of map, categories and uses of maps, marginal information, terrain features on map, how to orient a map, determine grid coordinate, determine elevation, determine azimuth, methods of holding a lensatic compass, and back azimuth. Next, determine distance. And lastly, methods of point location, polar plot, intersection, and resection. For the lesson objective, to provide the MS2 ROTC cadets the knowledge and develop their skill in map reading and to impart to them the importance of map information in the future planning. First is the definition, importance, and caring of map. What is a map? Comes from Latin word mappa, meaning napkin or paper. A map is a graphic representation of the Earth's surface that's seen from above, or the bird's eye view. It also uses colors, symbols, and labels to represent features found on the ground. Also, a map provides information on the location, the distance, the routes, elevation, and various terrain features, natural and man-made. Here are some lists of importance of map. A map can give accurate information. It gives you guide on a specific place, showing a glimpse of what you can see, such as the mountains, rivers, and shape of the place. It becomes more and more necessary to rely upon a maps, more significantly to the places you are not familiar with. Next, by necessity, planning must be done on maps. During operations, map is a must. It shows the terrain features of the place, such as the shape of the place, the rivers, and vegetations. With that, military personnel can move easier. And lastly, we must have adequate supply of maps. We must also secure our maps. All maps should be considered as documents that requires special handling. If a map falls into unauthorized hands, it could easily endanger military operations by providing information of friendly plans or areas of interest to the enemy. Caring of maps. Maps should be protected from water, mud, and tearing. Maps should be carried in waterproof cases. in pocket or in place where it is handy for use but is still protected. And if you put a marker on a map, use pencil, so you could erase it easily. Next is the categories, types, and uses of map. Categories of maps. Maps are categorized according to scale, and there are three categories. First one is the small scale map. Map with the scale 1 is to 1 million and smaller, meaning 1 unit on the map distance is equal to 1 million meters ground distance. They are used for general planning and for strategic studies. Next is the medium scale map. Scales larger than 1 is to 1 million but smaller than 1 is to 75,000 are used for operational planning. They contain a moderate amount of detail, but terrain analysis is best done with large-scale maps. The standard medium-scale map is 1 is to 250,000. Next is the large-scale map. Those maps with scale 1 is to 75,000 and larger are used for tactical, administrative, and logistical planning. These are the maps the military are using. The standard large-scale map is 1 is to 50,000. However, many areas have been mapped at a scale of 1 is to 25,000, which is suitable for use by artillery units. Here is a representation on how the scale maps differs from each other. It shows that one spot on the map is enlarged, and as you enlarge the map, it also shows more details featured on the map. Next is the types of maps. The first one is planimetric map. Presents only the horizontal positions for the features represented, meaning it only shows the top view of the place. Next, topographic map. Maps that is commonly used by the military. It portrays terrain features in a measurable way. Shows both horizontal and vertical positions of the features represented, or show not only the top view but also the heights of the featured terrain by using contour lines. Next, photomap. A reproduction of an aerial photograph upon which grid lines, marginal data, place names, route numbers, important elevations, boundaries, and approximate scale and direction have been added. Next is the terrain model. A scale model of terrain showing features and in large scale model showing industrial and cultural shapes, or it shows the 3D view of the place. Next, it provides a means for visualizing the terrain for planning or indoctrination purposes and for briefing operations. Joint operations graphics. Maps based on the format of standard 1 is to 250,000 medium-scale military topographic maps that contain additional information needed in joint air-ground operations. Next, military city map. A topographic map usually at 1 is to 12,550 scale, sometimes up to 1 is to 5,000, showing the details of a city. Next is the special maps. Maps for special purposes such as trafficability, communications, and assault maps. Marginal information. Useful details about the map. First one is sheet name. In bold print located in the top center margin and lower left margin. It is the title of the map and is named after the largest geographical area represented. Next is sheet number. In bold print located in the upper right margin, lower left margin, and center box of the adjoining sheets diagram. It is used as reference number to link specific maps to overlays, operation orders, and plans. For maps at 1:100,000 scale and larger, sheet numbers are based on an arbitrary system that makes it possible to have ready orientation of maps at scale 1:100,000, 1:50,000, and 1:25,000, meaning that small scaled maps are divided to represent it in larger scale, and sheet number are used for each larger scaled map. The next one is series number. In bold print located in the upper right margin, lower left margin, and next to margin sheet numbers. It is a sequence reference expressed either as a 4-digit numeral or as letter, followed by a 3 or 4-digit numeral. In the regional grouping of allied mapping projects, our map series here in the Philippines was designated S. Series name. Found in bold print at the upper left corner of the margin. Usually includes a group of similar maps at the same scale and on the same sheet lines or format, designed to cover a particular geographic area. The name given to the series is generally that of a major political subdivision, such as state or nation. Next, bar scales. Located in center lower margin. Bar scales are rulers used to convert map distance to ground distance. Maps have 3 or more bar scales, each in a different unit of measure. And care should be exercised when using the scales, especially in the selection of the desired unit of measure. Contour interval note. Located in the center lower margin, normally below bar scales. The contour interval note states the vertical distance between adjacent contour lines of the map. When supplementary contours are used, the interval is indicated. In recent edition maps, the contour interval is given in meters instead of feet. Adjoining sheets diagram. Maps at all standard scales contain a diagram that illustrates the adjoining sheets. Next, elevation guide. This is normally found in the lower right margin. It is a miniature characterization of the terrain shown. The terrain is represented by bands of elevation, spot elevations, and major drainage features. Grid reference box. Located in the center lower margin. The box contains instructions for composing a grid reference. Unit imprint. Identifies the agency that prepared and printed the map with its respective symbol. This information is important to the map user in evaluating the reliability of the map. Declination diagram, located in the lower margin, indicates the angular relationships of true north, grid north, and magnetic north. True north. A line from any point on the Earth's surface to the North Pole. All lines of longitude are true north lines. The true north is usually represented by a star. Magnetic north. The direction to the North Magnetic Pole, as indicated by the north-seeking needle of a magnetic instrument. Magnetic north is usually symbolized by a line ending with a half arrowhead. Grid north, the north that is established by using the vertical grid lines on the map. Grid north may be symbolized by the letters GN.
Next, legend, located in lower left margin. The legend illustrates and identifies the topographic symbols used to depict some of the more prominent features on the map. The symbols are not always the same on every map. Always refer to the legend to avoid errors when reading a map.
Legend includes topographic symbols. Topographic symbols represents the natural and man-made features of the Earth's surface. These are some examples of topographic symbols. Colors on military map. Red depicts classification of roads, built-up areas, and special features. Blue, water features such as lakes, swamp, rivers, and drainage. Green, represents vegetation. Black, represents man-made objects, that is buildings, towers, and etc. Next, brown, depicts relief and elevation, such as contours on older maps and cultivated land. Identify terrain features on a map. When reading a map, you must be able to identify all terrain features regardless of the contour interval. You must also be able to recognize all of the terrain features in order to locate a point on the ground or to navigate from one point to another. There's mainly 5 major terrain features: the hill, valley, ridge, saddle, and depression, and 3 minor terrain features: draw, spur, and cliff, and 2 supplementary terrain features: the cut and the fill. First is hill. Hills are represented by contour lines forming concentric circles. You can use your fist to help remember and visualize terrain features. A heel looks like one of the knuckles of your fist. A hill is a major terrain feature. Next, valley. Valleys usually have maneuver room and contain a stream or river. Valleys are depicted as contour lines forming a U. The lines tend to parallel a stream before crossing. The contour line crossing a stream always points upstream. And you can visualize a valley as your open hand. A valley is a major terrain feature. Next, ridge. Ridges are depicted as contour lines forming a U or V. The close end of a contour points away from a high ground. A ridge is a series of connected hills. You can visualize it as the four-knuckle of your fist. Next, saddle. A saddle can be either lower ground between two hills or a break in a level crest. A saddle is depicted as an hourglass. You can visualize saddles as the spaces between the knuckles of your fist. Next, depression. A depression is depicted by close contour lines that have thick marks pointing towards lower ground. You can visualize a depression as your open hand with your palm cupped slightly. Next is the cliff. Cliffs are depicted by contour lines drawn close together or by thick or carrying contour lines. Thick points to lower ground. You can visualize a cliff as the outside edge of your fist. Next, draws. Draws are depicted as contour lines shaped like a V with the point of the V towards the head or high ground of the draw. You can visualize draws as the spaces between your fingers running down from the spaces between the knuckles of your fist. Draw is a minor terrain feature. Next, spurs. Spurs are often formed by parallel streams cutting draws down a ridge. Spurs are depicted by U or V-shaped contour lines with U or V pointing away from high ground. You can visualize spurs as the slopes of your fingers running downhill from the knuckles of your fist. Next is the supplementary terrain features. First one is cut. A cut is a man-made feature resulting from cutting through raised ground, usually to form a level bed for a road or railroad track. Cuts are drawn with a contour line along the cut line. This contour line extends the length of the cut and has tick marks that extend from the cut line to the roadbed, if the map scale permits this level of detail. Next is the fill. A fill is a man-made feature resulting from a filling a low area, usually to form a level bed for a road or railroad track. Fills are drawn with a contour line along the fill line. To better understand about terrain features, here is the interpretation of the terrain features. Orient a map. To check that you have your map oriented correctly, Place your compass along the north or south grid lines, with the top of the compass pointing toward the top of the map. Then, rotate the map and compass together until the compass points north. This will ensure you are not on the opposite side of what you are looking at. Then, adjust for declination according to the margin of the map.
As a member of a squad or team in a field environment, you will need to know how to orient a map in preparation for movement. For this task, you will have a 1 to 50,000 scale topographic map of the area and a compass. The first step for a navigator in the field is orienting the map. A map is oriented when it is in a horizontal position with its north and south corresponding to the north and south on the ground. When orienting a map with a compass, remember that the compass measures magnetic azimuths. Since the magnetic arrow points to magnetic north, pay special attention to the declination diagram. Special care should be taken when orienting your map with a compass. A small mistake can cause you to navigate in the wrong direction. Once the map is oriented, magnetic azimuths are determined using the compass. Do not move the map from its oriented position, since any change in its position moves it out of line with magnetic north. You must determine the direction of the declination and its value from the declination diagram on the map. Lay the map in a horizontal position. There are two techniques that can be used to orient the map. For the first technique, take the straight edge on the left side of the compass and place it alongside the north-south grid line with the cover of the compass pointing toward the top of the map. This procedure places the fixed black index line of the compass parallel to the north-south grid lines of the map. Keep the compass aligned as instructed while rotating the map and compass together until the magnetic arrow is below the fixed black index line on the compass. At this time, the map is close to being oriented. Rotate the map and compass in the direction of the declination diagram. Next, verify the GM angle. If the magnetic north arrow on the map is to the left of the grid north, check the compass reading to see if it equals the GM angle given in the declination diagram. If the magnetic north is to the right of grid north, check the compass reading to see if it equals 360 degrees minus the GM angle. If the GM angles are correct, the map is oriented. To orient a map using the second technique, begin by drawing a magnetic azimuth equal to the GM angle given in the declination diagram with the protractor, using any north-south grid line on the map as a base. If the declination is westerly or to the left, the drawn line will equal 360 degrees minus the value of the GM angle. Align the straight edge on the left side of the compass alongside the drawn line on the map. Then rotate the map and compass until the magnetic arrow of the compass is below the fixed black index line. The map is now oriented. If the declination is easterly or to the right, the drawn line is equal to the value of the GM angle. Using one of these two simple techniques with a map and lensetic compass, you can easily orient a map in preparation for movement.
Determine the grid coordinates of a point on a military map. The military map is composed of two lines. First is the vertical lines drawn from top to bottom, or the blue lines. Another one is the horizontal lines drawn from left to right, or the red lines. These lines form small squares 1,000 meters on each side, called grid squares. The lines that form grid squares are numbered along the outside edge of the map picture. And no two grid squares will have the same number. Precision of grid coordinates. The precision of a point location is shown by the number of digits in the coordinates. 4-digit grid square coordinate, or 1,000 meter precision, meaning Each side of the square measures 1,000 meters. 6-digit grid square coordinate, meaning your location is in 100-meter precision, or the 4-digit grid square is divided into 100 square, 10 squares on each side. Each square measures 100 meters by 100 meters. Next is the 8-digit grid square coordinate. Your location is in 10-meter precision, or the 4-digit grid square is divided into 10,000 square, 100 squares on each side, and each square measures 10 meters by 10 meters. And lastly is the 10-digit grid square coordinate, the most precise and accurate determination of location, meaning you divide the 4-digit grid square into 1,000,000 square, 1,000 squares on each side, and each square measures 1 meter by 1 meter. A 4-digit grid coordinate. A 4-digit grid coordinate will get you within 1,000 meters. To determine your location, start at the bottom left corner of each grid square. Do the read right and up to get the coordinate of each square. Six-digit grid square coordinate. To make your location more accurate, just add another number to the first half and another number to the other half so your address has 6 numbers instead of 4. Suppose that each grid square has 10 lines inside it, running north and south, and another 10 running east and west. This makes 100 smaller squares. You can estimate where these imaginary lines are. Suppose you are halfway between vertical grid line 02 and 03. This means the next number is 5 and the first half of your 6-digit grid is 025. Now, suppose you are 7/10 the way up between horizontal grid lines 82 and 83. This means the second half of your 6-digit grid is 827. The additional numbers also use the read-write-up method. The first additional number is from the vertical grid lines, that is read from left to right. And the last number is from the horizontal grid lines, read from the bottom to top. Eight-digit grid coordinate. The most accurate way to determine the coordinates of a point on a map is to use a coordinate scale. You do not have to use imaginary lines because you can come up with the exact coordinates. In this example, we want to find the 8-digit coordinate of point A. First, locate the grid square in which point A is located. In this example, point A is located in grid square 0282. Next, place the coordinate scale on the bottom or at the horizontal grid line and to the left side of the grid square. Both the horizontal and vertical zeros should be in at the bottom left corner of the grid square. To find the coordinates, slide the coordinate scale to the right until you match the vertical scale next to the point. Make sure you keep the horizontal scale and the horizontal grid line parallel and line up. Where the left grid line crosses, the horizontal scale is where you get the horizontal coordinate. In this example, it reaches 59. Where the point crosses the vertical scale is where you get the vertical coordinate. In this example, point A reaches 31 on the vertical scale. So, the 8-digit coordinate for point A is 02598231. Determine two-letter 100,000 meter square identifier. To determine the correct two-letter 100,000 meter square identifier, look at the grid reference box in the margin of the map. When reporting across a 100-meter line, prefix the 100-meter square identification in which the point lies. In this example, grid coordinates located above the 00 grid line would be prefixed with EH, and grid coordinates located below the 00 grid line would be prefixed with EG.
The military grid system is a network of squares formed by the north-south and east-west grid lines printed on a map. The purpose of the grid system is to enable the soldier to quickly and accurately locate a point on a map. This video focuses on determining the coordinates of the grid square, determining grid coordinates of a point with and without a coordinate scale and protractor or plotting scale, and identifying the 100,000 meter square identifier to determine a grid coordinate. Determine the coordinates of the grid square. Select the grid square that contains the identified point on the map. Always begin your reading from the southwest corner. Read the north-south grid line that precedes the desired point, and record the number associated with that line. Read the east-west grid line that precedes the desired point. Record the number associated with that line. The number of digits represents the degree of precision to which a point has been located and measured on a map. The more digits, the more precise the measurement. In the above example, the 4 digits 1181 identify the 1,000-meter grid square to be used. Determine the point grid coordinates without a coordinate scale and protractor or plotting scale. Allocate the grid square into a 10 by 10 grid. Read right from the lower left corner to the imaginary grid line nearest the identified point. In the example, the north-south imaginary line nearest the point is halfway, or 5 lines out of a total of 10 lines. Therefore, the first half of your grid coordinate is 115. Read up from the first point reached to the imaginary grid line nearest the identified point. In the example, the east-west imaginary line nearest the point is 1/3 of the way up, or 3 lines out of 10 lines. Therefore, the second half of your grid coordinate is 813. Determine point grid coordinates with coordinate scale and protractor or plotting scale. The most accurate way to determine the coordinates of a point on a map is with a coordinate scale. You need not imagine lines because you can find the exact coordinates using the coordinate scale and protractor or plotting scale. Each device includes 2 coordinate scales, 1 to 25,000 and 1 to 50,000 meters. Make sure that regardless of which device you choose the correct scale. Locate the grid square where the point is located. Determine the coordinates of the grid square. The number of the vertical grid line on the left or west side of the grid square gives the first and second digits of the coordinate. The number of the horizontal grid line on the bottom or south side of the grid square gives the fourth and fifth digits of the coordinate. Determine the third and sixth digits of the coordinate. Place a coordinate scale and protractor or a plotting scale on the bottom horizontal grid line of the grid square containing point alpha. Check to see that the zeros of the coordinate scale are in the lower left-hand or southwest corner of the grid square where point alpha is located. Slide the scale to the right, keeping the bottom of the scale on the bottom grid line until point alpha is under the vertical or right-hand scale. To determine the six-digit coordinate, look at the 100-meter mark on the bottom scale, which is nearest the vertical grid line. This mark is the third digit of the number 115. The 100-meter mark on the vertical scale nearest to point alpha gives you the sixth digit of the number 813. The complete grid coordinate is 115813. Always read right and then up. There is a 100,000 meter square identifier, represented as a series of letters associated with each 100,000 meter square grid in the military grid reference system. Determining a location's 100,000 meter square identifier and adding the identifier to your grid coordinate allows you to specify and communicate a location on a map with greater precision. Add the 100,000 meter square identifier to the determined grid coordinate. Determine the 100,000 meter square identification by looking at the grid reference box in the margin of the map. Whenever a map covers multiple 100,000 meter square identification grids, as shown in this example, Foxtrot Lima, Golf Lima, and the first three digits are above 500, choose the left designator. If the first three digits are below 500, choose the right designator. Place the 100,000 meter square identifier in front of the grid coordinate. In the example given, the grid coordinate becomes Golf Lima 115813. Further location precision can be achieved by using the grid zone designation listed in the map's margin. Identify the grid zone designation 16 Tango in this example by looking in the grid zone designation box in the margin of the map. Place the grid zone designation 16 Tango in front of the 100,000 meter square identifier, Golf Lima, and the grid coordinate 115813. The final grid coordinate becomes 16 Tango Golf Lima 115813. By learning to utilize the grid system, you will be able to locate any point on a map in order to perform any number of land navigation tasks.
Determine elevation. Maps are flat but the ground isn't. To account for this and be able to measure land elevations, contour lines have been added to maps. Before we try to explain how the map determines elevation, the example to the left simplifies exactly how this contour line works. Contour lines. Contour lines connect a series of points of equal elevation and are used to illustrate topography or relief on a map. They show the height of the ground. For example, numerous contour lines that are close together indicate hilly or mountainous terrain. When far apart, they represent a gentler slope. Contour intervals. A contour interval is the vertical distance between two contour lines. The contour interval measurement given in the map's marginal information is the vertical distance between adjacent contour lines. The number index contour lines, which are circled in red in this example, state that particular line's elevation. Determine elevation. To determine a point's elevation, find the numbered index contour line nearest the point. Next, count the contour lines from the numbered line. This will tell you how many intervals to add or subtract from the numbered index contour line. In this example, the contour interval note states the distances between lines is 20 meters. Therefore, we can determine the elevations at each line by looking at the nearest numerical interval value. The elevation of point A is 260 meters and at point B is 280. Hilltops and depressions. For points at the top of hills, add half the contour interval. In this example, the hilltop's elevation is 370 meters. For points at the bottom of depressions, subtract half the contour interval. This depression's elevation is 230 meters. Shooting an azimuth. Use your compass to determine or follow an azimuth. The arrow on the compass points toward magnetic north. The arrow is also attracted by any mass of metal, for example, a truck, your rifle, your helmet, and even electrical power lines. Thus, be sure you use your compass away from metal objects so it will not give a wrong reading. The lensatic compass must always be held level and firm when sighting on an object and reading an azimuth. There are two methods of holding the lensatic compass and sighting: the compass to cheek and center hold method.
All right, so moving on, we have our compass here. It's a military issued lensatic compass. You'll notice I have a lanyard. Strongly encourage, always make sure that this compass is attached to your person. Here I have a thumb ring, and I'll show you how to use that here in a minute. If I turn over, I have the top plate here, as well as the base plate, and that just swivels on a hinge. If I turn my compass over, you'll notice this marking here, the model 3H Kamanga. That 3H signifies that all my illuminating lines are tritium as opposed to phosphorus. If I turn my compass over, you'll see the scale I have. It reads from 0 all the way out to 6,000, and that's a scale that's accurate on a 1 to 50,000 map, and it'll allow you to accurately read measurements all the way to 6,000 meters. On my top plate itself, I have a sighting wire here, and then I have a tritium line on the top and a tritium line on the bottom. Excellent use for low light conditions. Moving back to my base plate, I have a sighting mirror. That's not a mirror, it's a sighting glass, as well as a notch in the line which will be used for my sighting wire, and I'll show you how to use that here in a minute. It also has a magnifying glass here which will allow you to read your dial. So on the base plate, you see I do have a floating dial. You see how it kind of turns in every direction there. So this compass, and all good compasses are sealed, which protects it from the environment and different altitudes. So this top black ring you see here is called a bezel ring, and it will turn all the way around. And I'll show you why that's important. I'm going to turn this back to reset it here so it's in line with the fixed black line. So each click is 3 degrees. Every time you hear it click, hear or feel it click, it's moving 3 degrees. Down in here on the plate itself, of course I have my north-seeking arrow, which has a tritium line, and then my east and my west are marked. And underneath those you also have tritium lines as well. Again, useful for low light conditions. On the dial, you'll notice I have numbers in black and numbers in red. My numbers in black are mils. We're typically not going to use those for land nav. And then my numbers in red are degrees, and that's what we're going to be focusing on as we're doing land navigation and orienteering. All right. So another thing I want to tell you before we move on to something different here is that north-seeking arrow, of course, it's always going to point towards magnetic north. And if you get anything that's metal around your compass, it's going to mess you up, as you can see here, right? So I just got my knife here, and my north-seeking arrow is going to follow that knife all the way around. And so you want to make sure that you don't have any large metal objects on your person or near the compass. Make sure that you're looking at magnetic north, that it's going to always find magnetic north. All right, so let's get into how to use this compass. All right, so now that we just went over all the components of the compass, I'll show you how to use this thing. And there are two primary methods. The first method is compass to cheek method, and the second method is a center hold method. So for a compass to cheek method, I'm going to take my top plate and I'm going to rotate it back, trying to close it here, and I'm going to set it right till it's on top of my sight glass. And I'm going to take my thumb through the thumb loop, and then I'm going to bring the compass up to my eye, and I'm going to look through the sight glass and the sight wire until I can find the azimuth that I'm looking for. And all I have to do is look back down on my red dial, and when I look through my sight glass, I'm looking on the black fixed line that never moves on my base plate and find my azimuth. If I'm going to use the center hold method, I'm going to take my base plate and I'm going to open it all the way up until it locks out. I'm going to take my thumb, put it through the thumb loop, and take both hands for security here, and I'm going to bring it right up towards my torso, again making sure I don't have any metal objects on my chest or on the front of my body. And let's just say I was trying to find 120 degrees. I'm going to rotate my body until I have 120 degrees is directly underneath my black fixed line. Once I have that set, I can take my bezel ring and I can rotate it until the illuminating line on my bezel ring and the illuminating line on my north-seeking arrow are perfectly in line. And then that way, as I start moving towards my objective, if I start to drift left or drift right, I can always just look up at look down at my compass. And if those lines are in place, I know that I'm good. If they start to drift left or drift right, my north-seeking arrow, because it's always pointing north, that's going to tell me that I'm not moving in the right direction. So that's how you're going to preset a compass. Let's take a closer look at how each one of those looks like. All right, so now I'll show you how to do each method as it's going to look from your own perspective. And for demonstration purposes, I'm going to use this pole right out here directly in front of me. For the compass to cheek method, I'm just going to bring the compass up to my eye, and I'm going to line that pole on that siding wire and that notch stake, and then I can look down and read what the azimuth is on my compass, and then I can preset it, and I'll show you how to do that here in just a second. For the compass to cheek, or as you were, compass to cheek, we just did that one. So for the center hold method, I'm just going to bring the compass up to my torso, and I'm going to shift left or twist right until that pole, until this black line on my bezel ring that doesn't move is in line with that pole. And then to preset my compass, I just turn my bezel ring until the illuminating line on my bezel ring and the illuminating line on my north-seeking arrow are in line. Now once I start moving, as I said before, I can move, and all I have to do is just take a glance down and make sure that those lines are together. If I start moving and I look up and I see that all of a sudden my lines aren't lined up anymore, I know I'm moving in a different azimuth. So I just reorient myself, wait till they line back up again, and then start moving again. If they shift off to the other direction, it's too easy. Just rotate back until they're in line, and then now we're good to go.
In this lesson, I will demonstrate how to correctly hold the compass using the center hold technique. The center hole technique is less precise, but is faster to use and can be used under all conditions of visibility. First, open the cover until it forms a straight edge with the base. Pull the rear sight to the rearmost position, allowing the dial to move freely. Next, place your thumb through the thumb loop. Form a steady base with your third and fourth finger and extend your index finger along the side of the compass. Place the thumb of the other hand between the rear sight and the bezel ring. Extend the index finger along the remaining edge of the compass and the remaining fingers around the fingers of the other hand. Place your elbows in firmly into your sides. This will place the compass between your chin and your belt. To measure an azimuth, turn the entire body toward the object, pointing the compass directly at the object. Once you are pointing at the object, look down and read the azimuth from the fixed black index line. In this lesson, I will correctly demonstrate how to hold the compass using the compass to cheek method. First, you open the thumb loop. Then you will open up the cover to the compass until it's at about a 90-degree angle to the compass. Then you will open the lens or the eyepiece until it's about a 45-degree angle to the compass. Then you will place the thumb of your dominant hand through the thumb loop, wrapping the index finger around the compass and curling the rest of the fingers up under the compass. Then you will take your non-dominant hand and cup your dominant hand. Then you will bring both hands in the compass up to your face, to your dominant eye, and you've already determined your azimuth. So you will look through the eyepiece, find your azimuth, align it with the sighting wire in the cover to the point with which you're trying to move on your azimuth. This is the correct method of holding the compass to cheek.
Find an azimuth on a map. First, lightly plot the location of the 2 points on the map using a pencil. Next, use a straight edge to draw a thin line between both points. The line must be long enough to cross the scale on the protractor. Then, place the center of the protractor over your first point. Also, ensure the protractor is squarely placed on the map or else your results may be off. Next, look to see where your drawn line crosses the edge of the protractor. Be sure to use the correct scale, whether it's degrees or mils. In this example, it is 62 degrees from point A to point B. Converting azimuths. You cannot follow a grid azimuth with a compass, nor you cannot plot a magnetic azimuth with a protractor. To assist you in making the conversion from magnetic north to grid north, and vice versa, a declination diagram is placed on the margin of your map. The angular difference between grid north and magnetic north is called the GM angle. For this particular map, the GM angle is 21 degrees. Simply read the directions in the diagram when you need to convert the angles for the particular map. For example, you get 200 degrees magnetic azimuth on your compass, and you need to plot it on your map. So, to get its grid azimuth or grid north, add 21 degrees or add the GM angle. Then, it is equal to 221 degrees grid azimuth. However, if you get 45 degrees grid azimuth and you need to follow the direction of your compass, you must know its magnetic azimuth. So, subtract its GM angle, or for example 21 degrees, Then you will get 24 degrees magnetic azimuth. Back azimuth. Suppose you are heading 65 degrees, but you need to come back to where you started. Instead, replotting your points, you can simply reverse your direction 180 degrees to find your back azimuth. In getting the back azimuth, if the number is less than 180 degrees, add 180. And if the number is greater than 180 degrees, subtract 180. For example, measuring distance. A bar scale is a ruler printed on the map and is used to convert distances on the map to actual ground distances. To the right of the zero, the scale is marked in full units of measure and is called the primary scale. To the left of the zero, the scale is divided into tenths and is called the extension scale. Using a bar scale. First, align the right side of measurement to the nearest thousands. On the left side, count the hundreds. Then, imagine one of the extension blocks into tenths and estimate which tenth the left side is at. Below is an example of how the bar scale works. Determine straight line distance. For a straight line distance, simply use the edge from a piece of paper and mark distance between the 2 points. Next, line the paper up to next scale to determine distance. In this example, the distance between point A and point B is approximately 3,000 meters. Determine curved road distances. With a curved line, break the curve into series of straight lines and measure from curve to curve. To estimate more accurately, line up the right side of your marks to the nearest thousands. You can use the extension scale to the left of the zero to be more precise. In this example, the distance from point A to point B is approximately 2,580 meters. Polar coordinate. In polar coordinate, we plot azimuth from a known point, plot distance from the known point along the azimuth line, and the polar coordinate is at the end of the azimuth or the distance line. For the steps in getting the polar coordinate, step 1, place the index mark of the protractor at the center of mass on the point from which you are measuring. Step Step 2. Locate the desired azimuth on the protractor scale and place a dot on the map at this azimuth. In this example, they choose 56 degrees. Then, remove the protractor and connect the point and dot with straight line. For the next step, select the appropriate scale measurement and place a paper straight edge on the scale. Example, you choose the distance in meters. Then, determine the desired distance to measure from the scale and mark the paper at the distance using tick marks. In this example, they choose 3,400 meters. Next, align the straight edge with the azimuth line. Ensure the first tick mark is center mass on the known point. Then, place a dot on the map at the second tick mark from the straight edge on the map. The position of the second tick mark is the position of the unknown point. Next, remove the straight edge and determine the grid coordinate to the second point. In this example, we get the polar coordinate e.g. 15.8, 82.1. Next, intersection. Our objective for this is to determine the position of an unknown point by occupying at least 2, but preferably 3 known positions. Next, determine the azimuth to the unknown point from these positions. And plot the azimuths from the position to locate the unknown point by their intersection. Step 1. Sight the unknown point on the ground. Then, locate your position on the ground and mark it on the map. Step 3. Determine the magnetic azimuth from the road junction to the enemy position. Step 4. Convert the magnetic azimuth to grid azimuth, for we need the grid azimuth when plotting on map. For example, we get magnetic azimuth 59 degrees. So, we need to add the GM angle, for example 21 degrees. So, the grid azimuth will be 80 degrees. Then, step 5, draw a line from the road junction along the 80-degree grid azimuth. Step 6, move to, or preferably, radio a second position from where someone can see the unknown point, and mark the position on the map. Step 7. Determine the magnetic azimuth from the second road junction to the enemy position. Also, convert the magnetic azimuth to grid azimuth. Step 9. Draw a line from the second road junction along the 100-degree grid azimuth. Step 10. Where the lines cross is the location of the unknown point. In this example, we can say that the location of the unknown point is e.g. 16108055. It's desirable to repeat the procedure from a third point to increase the accuracy. For example, your third point is located at road junction at e.g. 15478180. Its magnetic azimuth is 128 degrees. So, convert it to grid azimuth. Notice that the lines from the first and second point form a shallow angle. This decreases accuracy. Whenever possible, choose the location that will give you a larger angle, closer to 90 degrees like position. But, when triangulating, record the center of the triangle as the location. In this example, the location of the unknown point is e.g. 16208055.
Intersection is a method to locate something unknown from one or more known places. Either calculating the grid location of an object in the distance or finding your own location, this technique will prove essential during land navigation. Performing intersection is not hard as long as you focus and take your time. There are two methods of intersection: map and compass and straight edge. Both techniques allow you to locate a point that you do not know the coordinates of. The map and compass method of intersection is used to find the location of an unknown point by getting the direction of that unknown point from two or more known points. Orient the map on a flat surface using a compass. Plot grid azimuths from known points to the unknown point on the map. Mark your position on the map. Determine the magnetic azimuth from your position to the unknown point. Convert the magnetic azimuth to a grid azimuth. Place the index point of a protractor on your plotted position. Align the protractor's 0 to 180 degree line to the top on the map's north-south grid line. Ensure the 0 degree mark is pointing to the north or top of the map. Place a tick mark on the map beside the number on the protractor that corresponds to the computed grid azimuth. Draw a straight line from your plotted position to the tick mark and beyond. Repeat all of these steps for each observer position. Identify the point where the lines intersect as the location of the unknown point. Determine the grid coordinates to this location to the desired accuracy.
The next one is resection. First, determine the position of an unknown point by sighting on at least two, but preferably three known positions. Next, determine the azimuths from the unknown point to this position. And lastly, plot the back azimuths from the known positions to locate your unknown position by their intersection. Next, we should know how to get the back azimuth. Rule number 1. If the azimuth is more than 180 degrees, then subtract 180 degrees. Rule number 2. If the azimuth is 180 degrees or less, then add 180 degrees. Step 1. Locate a feature or object that is identifiable on both the ground and the map and mark the map location. Step 2. Measure the magnetic azimuth to the known position and convert the magnetic azimuth to a grid azimuth. Step 3. Change the grid azimuth to a back azimuth and draw a line from the known position backward toward your unknown position. In this example, we have a grid azimuth of 50 degrees, and to convert it to back azimuth, add 180 degrees. Step 4. Locate a second feature or object that is identifiable on both the ground and the map and mark the map location. Example, bridge located at EG 1500-8389. Step 5. Measure the magnetic azimuth to the second known position and convert the magnetic azimuth to a grid azimuth. In this example, we get 151 degrees magnetic azimuth, and to convert it to grid azimuth, add the GM angle. Step 6. Change the grid azimuth to a back azimuth and draw a line from the second known position backward toward your unknown position. Step 7. The point where the two lines intersect is your location. In this example, we get the grid coordinate EG 1485-8494. Step 8. For a check on accuracy, you should construct a third line following the steps as outlined. Whenever possible, choose locations that will give you a larger angle where the lines intersect to increase accuracy.
Resection is a method to locate something unknown from one or more known places, either calculating the grid location of an object in the distance or finding your own location. These techniques will provide essential during land navigation. Performing resection is not hard as long as you focus and take your time. There are two methods of resection: map and compass, and straight edge. Both techniques allow you to locate a point that you do not know the coordinates of. Resection is used when you need to figure out where you are and you can see at least two terrain features or objects that appear on your map. The more objects you use, the greater the accuracy of your calculations. For the map and compass method, orient the map on a flat surface using a compass. Identify at least 2 well-defined points on the ground. Mark these well-defined points on the map. Plot the back azimuths on these points on the map. To compute a back azimuth, determine the magnetic azimuth from your location to one of the defined points. Convert the magnetic azimuth to a grid azimuth. Convert this grid azimuth to a back grid azimuth. Place the index point of the protractor on the well-defined point. Align the protractor's 0 to 180 degree line to the top of the map's north-south grid line. Ensure the 0 degree mark is pointing to the north or top of the map. Place a tick mark on the map beside the number on the protractor that corresponds to the computed back grid azimuth. Draw a straight line from the well-defined point to the tick and beyond. Repeat these steps for each well-defined point. The point where your lines cross is your current location. Determine the grid coordinates to this location to the desired accuracy.
In summary, we have learned about the definition, importance, and how to take care of a map, the categories and uses of map such as the small, medium, and large-scale maps, marginal information or the important details and guides on map. Next is the terrain features on map. Next is to how to orient a map. Next is determine grid coordinate such as 4-digit grid coordinate and 6-digit grid coordinate. Next, determine elevations or the use of contour lines on map. Also, determining the azimuth, the two methods of holding a lensatic compass, namely the compass to cheek method and center hold method. Also, determining the back azimuth. We've also learned about determining the distance or how to use the bar scales. And lastly, the method of point location, the polar plot or polar coordinate method, the intersection and resection.